Hey, science fans, let's talk about something that powers our world. Quite literally, the power transformer. Think of it as the unsung hero of the electrical grid. It's a big, usually gray box you see in substations, and its job is to change the voltage of electricity. This is super important because electricity is sent over long distances at very high voltages to save energy, but it needs to be stepped down to a much lower, safer voltage before it can power your computer or charge your phone. A transformer does this with some really elegant physics. It's essentially two coils of wire, the primary and secondary windings, wrapped around a shared iron core. It's an amazing piece of engineering, working silently day and night. The magic happens through something called electromagnetic induction. When alternating current, or AC, flows through the primary winding, it creates a changing magnetic field in the iron core. This magnetic field is like an invisible, pulsing river of energy. We call this river magnetic flux. Because the iron core guides this flux, it flows right through the secondary winding. This changing magnetic flux then induces a voltage in the secondary coil, causing current to flow. The ratio of turns in the primary coil to the secondary coil determines whether the voltage is stepped up or down. It's a beautiful dance of electricity and magnetism, all contained within that steel box. Under normal conditions, this magnetic flux is well behaved. It stays neatly confined within the laminated steel sheets that make up the transformer's core. The core is designed to handle a specific amount of flux, just like a pipe is designed to handle a certain amount of water flow. The flux density, how concentrated the magnetic field is kept at an optimal level. This ensures the transformer operates efficiently, transferring power with minimal losses. The whole system is in a state of happy equilibrium, humming along quietly as it performs its critical function of managing electrical energy for all of us. The relationship that governs this whole process is simple but profound. The magnetic flux, often represented by the Greek letter phi, is directly proportional to the voltage applied to the winding and inversely proportional to the frequency of the AC power. This gives us the famous relationship flux is proportional to voltage over frequency. This voltage over frequency ratio is the golden rule for transformer operation. As long as this ratio stays within the transformer's design limits, the magnetic flux behaves, the core does its job perfectly, and the lights stay on. It's a delicate balance that electrical engineers work very hard to maintain across the entire power grid. So, what happens when that perfect voltage over frequency balance is disturbed? Imagine our well-behaved river of magnetic flux turning into a raging, overflowing flood. This is what we call over-fluxing, or over-excitation. It happens when the voltage over frequency ratio exceeds the transformer's design limit. This can occur in one of two ways. Either the voltage gets too high while the frequency stays the same, or the frequency drops while the voltage remains constant. In both scenarios, the result is the same. The transformer is forced to create more magnetic flux than its core was ever designed to handle. It's a recipe for trouble. When the core is asked to carry this excess flux, it reaches a point called saturation. Think of a sponge that's already completely soaked with water. If you try to add more water, it just spills out everywhere because the sponge can't absorb anymore. The transformer's iron core is just like that sponge. It has a finite capacity for magnetic flux. Once it's saturated, the extra flux can't be contained within the core anymore. It starts to spill out into the surrounding structures of the transformer, like the tank, the clamps, and even the windings themselves, places where it's not supposed to be. This rogue flux creates a chaotic scene inside the transformer. Instead of smooth, orderly lines, the magnetic field becomes dense and distorted. The spilling flux induces unwanted currents, called eddy currents, in the metallic parts that aren't designed to handle them. This internal chaos doesn't stay quiet. The intense magnetic forces cause the transformer's core, laminations, and structural parts to physically vibrate. The gentle, steady hum of a normal transformer escalates into a loud, menacing growl or a deep, unsettling groaning sound. This audible noise is a clear distress signal that the transformer is operating under severe stress. The mathematical relationship, flux is proportional to voltage over frequency, clearly shows us the problem. Let's say a transformer is designed to operate with a voltage over frequency ratio of 1. If a grid disturbance causes the voltage to rise by 10% while frequency is stable, the ratio becomes 1.1. The flux has increased by 10%. Or, consider a generator that is slowly starting up. Its frequency might be low, say 0.9, while its voltage is at the normal level of 1. The voltage over frequency ratio becomes 1 divided by 0.9, which is approximately 1.11. Again, the flux is over 10% higher than it should be. The core simply can't handle it, and the over-fluxing frenzy begins. An over-fluxed transformer is a very unhappy transformer, and the consequences can be severe. One of the most immediate and dangerous effects is rapid core heating. Remember those stray flux lines spilling out of the saturated core? They induce eddy currents in the core's steel laminations and other metallic components. These currents generate a tremendous amount of heat due to electrical resistance, a phenomenon known as I²R heating. This isn't the normal manageable heat from standard operation. This is intense, concentrated heating that can raise the core's temperature to dangerous levels in a matter of minutes or even seconds if the over-fluxing is severe enough. This extreme heat is a direct threat to the transformer's most vulnerable component, its insulation. The windings are coated with insulating paper and enamel, which are then submerged in oil. This insulation is designed to last for decades under normal temperatures. However, when subjected to the extreme heat from over-fluxing, the insulation begins to degrade rapidly. It can become brittle, crack, and lose its dielectric strength. This is like aging the transformer by years in just a few moments. Once the insulation is damaged, it can lead to short circuits between windings or between a winding and the core, resulting in a catastrophic failure. At the same time, the transformer's magnetizing current skyrockets. Under normal conditions, the magnetizing current, the current needed to create the flux in the core, is very small, usually less than 1% of the transformer's full load current. But when the core saturates, it becomes much less effective at carrying flux. The transformer desperately tries to create the required flux by drawing a huge amount of current from the power source. This magnetizing current can increase by 10, 50, or even 100 times its normal value. This distorted, spiky current waveform is also rich in harmonics, which are unwanted frequencies that can disrupt other equipment on the power grid. This combination of intense core heating, insulation stress, and massive distorted currents puts the entire transformer system in jeopardy. The high currents can trip upstream breakers, but the real danger is the thermal damage. The heat can cause the insulating oil to break down, producing flammable gases that can build up pressure inside the tank. If the condition persists, the pressure can become so great that it ruptures the transformer tank, leading to an oil fire or an explosion. It's a dramatic and costly failure, all starting from that simple voltage over frequency ratio going out of bounds. This is why understanding and preventing overfluxing is so critical for a reliable power system. Given the serious dangers, how do we protect these vital pieces of equipment? We can't just cross our fingers and hope the voltage over frequency ratio stays perfect. Electrical engineers use sophisticated protective devices called voltage over frequency relays, or ANSI device number 24. These relays are the dedicated guardians of the transformer. They continuously monitor the voltage and frequency of the power supply, calculating the voltage over frequency ratio in real time. Their sole purpose is to detect when this ratio exceeds a safe, predetermined level and to take action before any permanent damage can occur. They are the brain behind the transformer's self-preservation system. There are several real-world scenarios where these relays are essential. One common cause is a large load being suddenly disconnected from the grid, which can cause the system voltage to rise. This is called the Ferranti effect on long lines. Another is during the startup or shutdown of a generator connected to the transformer. As the generator spins up, its frequency is low, creating a high voltage over frequency ratio. A similar situation occurs during shutdown. Operator error, such as selecting the wrong tap on a transformer's tap changer, can also apply an incorrect voltage and lead to overfluxing. The voltage over frequency relay is designed to handle all these possibilities. Voltage over frequency protection typically works in stages. If the voltage over frequency ratio exceeds a lower threshold, say 105% of the nominal value, the relay might initiate an alarm. This alerts system operators that the transformer is under moderate stress, giving them time to investigate the cause and correct the situation manually. If the ratio continues to rise and crosses a higher, more critical threshold, say 110%, the relay doesn't wait. It takes decisive action by sending a trip signal to a circuit breaker. This instantly disconnects the transformer from the power source, protecting it from the damaging effects of severe overfluxing. It's a two-level defense system. Warn first, then act decisively. In summary, overfluxing is a serious condition where an excessive voltage over frequency ratio forces a transformer's core into saturation. This leads to a cascade of dangerous effects, including extreme core heating, insulation degradation, and massive magnetizing currents that can ultimately destroy the transformer. By understanding the simple voltage over frequency relationship and the real-world events that can disrupt it, we can appreciate the importance of protection. Thanks to smart devices like voltage over frequency relays, our power grid has a built-in defense mechanism that keeps these workhorses safe, ensuring that the electricity we depend on every day continues to flow reliably. It's science and engineering working together to keep our world